My name's Lydia Schiff, and I work at VSCO. And check it out. That's my little slide, my cool VSCO picture. And I work on imaging, photography, and video tools. And I write a lot of Renderscript for my job. And I'm really excited to talk about it. It's just, you'll see. I'm very enthusiastic about this technology. So VSCO is a art and technology company, and I work on tools that help people make art, and art is great, and so I really like it. Now, I'm gonna go over at the very beginning, what's the big idea? What am I trying to get across in this talk? If at the very least, I don't think anybody uses this technology. As far as I know, it's sort of a secret. But first of all, I want to say this is a real thing. It's in the Android SDK. If you type in like REND, it'll autocomplete. And it's this heterogeneous compute API. It was originally made for graphics, but it's not what it's used for anymore. But I want to give you some concept of what it is that you can do with it. Second thing, and this is the real motivation, like I can't stress this enough. Bitmaps are enormous, and this is the whole reason why we care about this technology at all. It's because, we'll get to that. Then the other thing would be like, as a very core intuition, if you have, why am I supposed to be using Renderscript at all? Why would I ever? And I think that the very first step should be, do you have a bitmap? Yes. Okay, this is probably a large enough allocation that you should consider potentially using some, parallelizing this computation if you're trying to edit it at all. The last thing would be, these script intrinsics is this phenomenal API that raises the Renderscript API up to the Java level. It's a high-level Java API that has phenomenal performance, and it should be something that sort of just clicks in your head automatically, like sort of your intuition should be like, oh, I want to blur something. Okay, cool. That's 4 lines of code. I use script intrinsic blur, and then I'm done, and I'm move on to the next thing. And then the other thing is that I wrote a camera app that is just going to use Renderscript to apply effects to video frames, and it's open source. I think it's a pretty good test harness for checking the performance and also rendering quality at different targets for particular Renderscript edits. And I have a video of it. I took a video. It's got my cat in it. And I show some edits, and I'll show you that in a little bit. So let's talk about, what are we talking about here? Options for compute on Android. What do we mean by compute here? It's sort of like, we have a lot of math to do. Phones are, in general, not particularly good computers. And so we might end up in a situation where maybe just running it, you've got a lot of work to do, maybe to just do it in Java. You can, but there's also, what we generally want to do in this case is look around for what are the processors, what is on this phone itself that we can take advantage of, where we're not just sort of making the phone really hot by grinding away on the CPU itself. So we can use Ginny, C, C++, so we can pass bitmaps, actually work quite nicely with the NDK. We could also use the GPU. So Canvas used to be a CPU API. It used to be backed by the Skia library, but no longer is hardware accelerated, which is kind of nice. There's also OpenGL ES2, which is a 3D rendering API. It's not really meant for computation, but you can use it in that way if you want to. You're sort of tricking it into doing math for you. And then there's Vulkan, if you so desire. Certain things like OpenGL is not supported. CUDA would be nice. It's sort of what it's meant for, GPU, but it is, requires NVIDIA devices. So for phones, this is not really going to be available. Renderscript, however, is somewhere in between. In fact, it's sort of, you're writing it in a way that is independent of the way it's actually written. Like, you're in charge of sort of writing the solution to the problem. I guess we'll get more into that. It can run in multiple places: CPU, potentially GPU, and also other processors that happen to be around. This is why it's called a heterogeneous compute API. Compute. It's not really Renderscript. It's a weird name. I think they should change the name. Anyways, this is, all right, so we're going to talk about this right now. What is Renderscript? And first, we have to talk about bitmaps. This is the real thing here. And I think that, okay. Bitmaps seem complicated. Who here has looked at not knowing exactly what to do with a bitmap? You look at the bitmap API, and it's like 2,000 lines long. It's been around forever. It sort of has something to do with canvases. You know that it's some big chunk of memory somewhere. You know, if you hear that these are big objects, like, you know, make sure that you cache these bitmaps, make sure that you try to reuse them, but also don't forget to release them and that sort of stuff. And I think what's most important about them is not that they're not that complicated to use. Sort of like the API is weird because like you can accidentally maybe use a different constructor than you were expecting, and you end up with something that is immutable and all these other things that you don't necessarily intend to do, and it makes the usage sort of, I don't know. You can get lost in the complexities of sort of like dealing with this object, but really it's just enormous. It's essentially, and it's instructive if you pass this down into NDK code. You get the NDK bitmap API gives you a pointer to the beginning of some buffer, and then a width and a height. And you're like, oh, it's just a big buffer of pixel data. That's the whole thing. That's really is what it is. But in particular, it's on Java heap. And this is important. So the two things are, yeah. So 4K image is 12 million pixels, which is almost 50 megabytes. That is huge, right? Am I right? When was the last time like you put in a pixel is 32 bits, so it's the size of an integer. It's packed like color information into an int, and you are asking for it. You go to the sort of grumpy guy who works at the counter at the in the kernel, and you're like, hey, cool, let me get some Java heap. And you ask for, he's like, oh yeah, sure, I can get you some Java heap. What do you need, Lydia? And I'm like, okay, well, cool. So, well, you have this really great camera. I like it. And thank you. I was like, okay, well, so really, I just want to decode this JPEG. So what I'm going to need is 12.5 million ints. Oh, actually, and I need 2 of them because I'm going to do some image processing. And in general, like, yeah, okay, maybe I want to do some edge stuff. I'm gonna want an input and an output. So go ahead and give me. Let me just go ahead and get, you know, two arrays each with 12.5 million ints in them. He's gonna be like, no, what are you talking about? Like, what do you think this is? This is a laptop? This is a Cray or something? Like, I'm not giving you 100 megabytes of managed heap. What are you talking about? And this is a phone issue. So it actually is. We hit a scaling problem on a phone. We're all of a sudden in a place where the bitmaps are fine to use, and if we downscale the bitmap, we can have 2 of them. But the number that we're talking about all of a sudden got so big that the API broke. Like, we literally, if you decoding this could be like a 4K image. Okay, that's fine. Cameras take 4K images. Like, you can definitely get one of those from you have a JPEG. It's about 3 megabytes, and you want to decode it, and you probably have enough heap to decode and get 1 of them, but you don't in general get 2. And so it all of a sudden breaks potential Java solutions for doing image processing because you can't have an input and an output. You need to, if you're going to have a second bitmap to act as the output, it needs to be not in managed heap, but elsewhere. And so that's just sort of the fact that bitmaps are in Java. But the other thing is that this is a huge array, and the reason what we're essentially going to be doing is iterating over a bunch of pixels. So it's maybe a for loop over a bunch of pixels, and we've got this inner loop sort of thing that we're trying to optimize. And we don't normally get a chance to do this on Android. Often the scope seems sort of can be almost depressingly small when we're working on phones. So it's like, okay, yeah, hey, okay, I got the right collection for the job right here. It's sorted. I'm going to use a tree set. I read about it in a blog post. I know that this is the right thing to use. And then you show it to somebody and they're like, okay, well, there's only like 10 things in that collection ever. So, I don't know, just put it in an array list and just do linear search or something like that. And you're like, oh, that sucks. Are you sure? Like, can't I can't I sort it or something? They're like, well, listen, time it or just, do whatever you want, but also ship this feature before we go out of business. And it's like, oh gosh, this is hard. We have hard jobs. But in general, there's engineering considerations where you can't spend all of your time optimizing inner loops as much as you might want to, because it's sort of a, fun sort of a thing for a programmer. Mostly, you have to have engineering justification for really digging in on a problem like this. And in this case, we do. This is a for loop that you essentially have a for loop where you're iterating over collection, and there is no bigger collection. I guess that's the point about bitmaps. I claim that this is the biggest chunk of memory you ever have on a phone ever. What else quite compares to this? So if there was ever a time to optimize an inner loop, it's when we're looping over I claim the biggest array that you ever deal with on a phone. So that is why we're talking about Renderscript. So let's talk a little bit about the API. Renderscript context. So this is like a context, a big sort of God object. We're familiar with these. In element. So when you're talking about mapping over something, you're mapping over a collection of elements. An element this is the type information for an element, talks about what its size is. They can be scalar or vector. So, a float 4. The one on the part of the left is the sort of Java class associated with it. And then on the right is the Renderscript runtime type. And so the bottom one right there is a pixel, RGBA 8888. And how you access it in the Renderscript runtime is as a char4. A type is the next thing. A type has an element, so it sort of describes an allocation. You're going to end up associating this with a raw buffer, and it's going to say, okay, eventually we're going to create an allocation, and an allocation has a type. So we're going to say, okay, cool. I'm going to create this type. I'm going to give it. I'd like it. This is the type of the bitmap that we were talking about earlier. It's going to be 4K. RGBA 8888, and we're going to create an allocation with that type. So the allocation itself is not in manage heap. This is going to be we're mallocing some memory, and what's nice about that is it doesn't count against us for purposes of out-of-memory errors, which is ideal. But we do, because we interact with it in Java, so we're associating this type information with it that will keep us from using this API incorrectly. So we still get a certain semblance of not static type safety, but it's type safe. It'll yell at us. It'll throw us pretty jarring runtime exceptions if we use it improperly, which is what we want because it's a sort of whatever we're doing, we want it to be correct, and it's a hard enough problem. So we're able to get the benefits of working with pointers essentially without getting a few extra checks on us. So the first top two parts that both create allocation in do the same thing. At the top, we're creating a type of this particular size from a bitmap. We're saying that it has bitmap type element, and then we are going to create an allocation, just mallocing some memory, and then we're copying the pixel data in. The second is we're creating it from a bitmap. So we're ending up with an allocation that, it's bitmap shaped, it's bitmap sized, but really what we're doing is just locking the bitmap in place. This is very similar to the NDK API, where you just sort of say, okay, it's somewhere in Java heap, don't move it. Also don't allocate it, keep it exactly where it is and just give me the actual address to the beginning of it. So the second part, it actually doesn't create any memory. It uses something called usage shared. And so there's also no copy, which is kind of cool. So it's essentially like doing a bytebuffer.wrap or any of the sort of wraps from the buffer API. And then eventually, we're going to have some scripts, take all the input, each element on the input, do something to it, write it into the output, and then we're going to copy from the output back into the bitmap. So what was that thing we did in between? Well, it's a script, like a render script. Get it? So let's say we have something that's like going to do grayscale. This is the execution strategy. This is a naive way of sort of iterating across these collections. And if we were going to do it in one thread, this is what we would do. This is what it would look like if you're doing it in, I don't know, Java, I guess, or C or C++. It'll end up being, if you're doing it in one thread, you're going to iterate across the pixels in scanline order and essentially call a function once per element. In this case, it's going to be pixels. So what you're essentially doing is you will do work is going to be some function somewhere that takes the value of the input at that space and also the x and the y, like the actual position of what element you're talking about, which is important because it's an image. You care about spatial information. We care about, I don't know, we care if it's on an edge, right? If we're perhaps averaging it, or if we're like, oh, we want to know if it's on an edge. We want to know if it's on an edge, like we're doing edge detection in the photo itself, or like, oh, it's in the top corner, so special consideration has to be taken for, because generally, okay, so this is the spatial information that would be important would be like, okay, this is the value here, and we also want the one above us, below us, to either side, or we want our whole sort of neighborhood, or we want to average it across several pixels, and doing so, we'll want to know where the x and the y is so that we can also do, texture lookups in these different locations. This is what now, I thought this was just a good title for a talk, but I think I want to define it. What does hello parallel mean? This is what it is. So some of these edits, let's call it a pixel edit or a point edit. What you're essentially doing is discarding the positional information because you don't care. So because it is a color in, color out. You're iterating over a bitmap and you're just saying, what's the color at that location? And you have some function that's going to take it maybe for grayscale. You're just getting the intensity and you're going to write in the gray value that you can interpret from that. But you don't care where it is. You're now just looking at the pixel itself, and your function is a function, like a pure function, capital P, capital F, pure function from int to int. That all of a sudden, so you sort of, it doesn't even matter that it's 2D anymore. We don't care. Width and height, we're just going to use that to figure out how the length of the array. And so we're mapping over an enormous allocation. This is going to run 12 million times potentially per draw. So, we can render 4K video with this. We could potentially, with that type of technology, and it'd be like 360 million calls to this function. But we're not really looping over it. This is how, conceptually, how it would work in one thread. But these can happen in any order. It doesn't matter. So we'll actually go back to the other one. The point would be that there are lots of execution strategies. By making that do work function right there, the logic itself is completely local. We only care about the value at that location and where it is. And for instance, so we're going for each row essentially. Cool. Put them each on a different thread, or put go in scanline order, or go in reverse order, or split it up into two pieces and do it on two threads, or put it on the GPU and do it in big chunks, or essentially what makes this a massively parallel problem, hella parallel problem, if you will, would be that you'll keep getting better speed up for however many cores you have up to the number of elements you have. So if we had 12 million cores, the whole thing would just be done all at once, and it's fine. But essentially, we have taken the time to perhaps answer the problem in such a way where the order of execution doesn't matter at all, which has given maximum flexibility to the Renderscript runtime to choose execution that is best for this particular device. Anyways, I don't know. That's wild. That's So these are different options. Actually, Canvas. So Canvas is one of the technologies we could use to do video processing. I think we could rule it out if the bitmaps are large enough. We don't want to. It's nice for a lot of things. It's sort of like it's an actual drawing technology, so you can do affine geometry and certain things that are not quite as easy in Renderscript. And it has a lot of examples, which is good. The issues are it's kind of hard. The bitmaps are on Java heap, so if you need 2 of them and you can't have 2 of them, you have to downscale the bitmaps. Oh, I forgot I had these slides. Yeah, complicated, big, huge. So the other option is the libgenie graphics, which is the NDK's bitmap API, which I guess, yeah, no, as we were saying earlier, you're able to lock the bitmap in place and just get a pointer to it, access the pixels directly. And then this fixes the allocation problem. You have a bitmap, you pass down a reference to it and lock it. You get a pointer to the beginning of it, and you also have the width and the height. So then you just malloc a buffer that's the same size, and now you have 2 of them. And this is a outside of managed heap allocation, so it doesn't count in the same way. So you can do it this. The difference is like it's only running on the CPU, but you can also there's a lot of existing code. The issues are the building's kind of hard. It's definitely slower. Considering the type of problems we're talking about are massively parallel, we want to perhaps get some of this work off the CPU so we're not just grinding away and making our phone real hot. And then Ginny is hard. It's, I don't know. Oh, perfect. Okay, I forgot I had this example. Yeah, this is what it would look like. And this is instructive for 2 reasons. One, it shows that, I don't know, what you get when you pass down this bitmap information is just a pixel, or just a pointer to the beginning of it, and then, a struct with the width and the height, pixel format, and that sort of thing, which makes you realize, oh, bitmaps aren't a big, complicated, enormous Java object with this huge API. It's just a big array. And then second, that it's not statically type safe. We pass down this thing, we get this Java object, the bitmap. We know it's a bitmap, right? But it's essentially what we get down there is the type information is still there, but if we don't check it, I don't know. And it's ugly. And that sometimes, so that J-class variable would be Ginny bitmap example.class, the object, reference to that, the class object. And some people call that variable class. Have you ever seen that? C-L-A-Z-Z? Don't do that. That's rough. Don't visit that. Yeah. Yikes. Another one, OpenGL. This is pure GPU. We use this at VSCO for, we just rewrote our pipeline to use OpenGL for video in particular, mostly because it plays nicer with media codec, which has, for various reasons. This is a 3D rendering API. What we would be using it for in a photo context is we're not really drawing. We're using it to do math. So essentially, what's nice is that for you want GLES2, it is available on all reasonable devices. So 14 and up, they have a real deal GPU. They have compatibility test suites that will yell at it if it's not able to sort of handle, GLES rendering. It really is very, 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 very fast, but it's, what else? It's nice. There's more examples. I think more people are used to it, but it is really hard. I know from just having learned it, my introduction had been from, as a application developer, was to all this sort of imaging stuff. I'm not an imaging person. I sit next to them. And the Renderscript made it sort of conceptually easy to kind of understand what it is that we were trying to do in order to compute these things fast. It's sort of, there's a very nice conceptual boundary between the problem itself and the execution. And for GLES, it's it's not there. It doesn't even know you're doing math. You're essentially you're doing all of you're setting up a 3D world that you're going to then, so it's a 3D world, so this is this rich sort of 3D immersive video game kind of thing that we're going to do. Okay, cool. Make a rectangle, 2 triangles, and then have it look directly at it and make sure that it fills the whole screen. Then take the whole image and just put that in one texture and then just draw it all at once. And like in the fragment shader, you can change the colors a little bit. But you're essentially, like, you're not even necessarily drawing anything. Like, if you happen to be showing it on the screen, it's kind of nice. We can use this, we can sort of render the edits as we go along, but possibly rendering off screen, you are talking about things as if they are textures even when they're not. And you also, it doesn't give you any help for this. It doesn't know what it is that you're trying to do necessarily, not for GLES 2. I think 3.1, and definitely like Vulkan, new APIs, they realize, oh, you're just trying to use general purpose computation because chip is useful for that, but GLES 2 is not aware of those things. So if you use certain extensions, you have to have a fallback if it doesn't work. And another possible thing, that we have another size issue here, which is occasionally phones, if you query a glmax texture size, the phone will tell you what the largest possible texture is. And if you sort of think about it in terms of, you're like, oh, I'll just put the whole image into a texture. Sometimes you can't do that. And so you need to have essentially, I don't know, a fallback on CPU, or you can tile if you want to, but depending on what you're doing, like something like shear perspective correct, that we're like, the geometry is pretty gnarly, and so what we'll do is, I guess, fall back to the reference implementation that's in C, and it's just really slow, and it's very obvious when you hit this sort of limit. You're like, oh, larger image, larger image, larger image, and then all of a sudden it takes like 12 seconds, and you'd be like, oh, that's how big of an image my the GPU can take. We also, there are phones, because cameras are very good, and the cameras, even on it doesn't like sort of, cameras and GPUs don't necessarily correspond to each other. You can end up in a situation where the camera takes these fabulous photos that are very big, and they are too large to fit on the GPU in a texture in one piece, which makes this a pathological situation if you are editing photos on a phone, that you'd be like, oh, I took a picture, and then, well, it instantly doesn't work. And you wouldn't expect this, because modern GPUs have something ridiculous like 16K texture buffers, but we've run into this in the wild. So like every single edit is really slow. I don't know. Let's see. Vulkan. I haven't used it. I heard it's really fast. I also heard it's really hard. It's 7.0 plus, so it'd be like only on the most modern devices. I think that Renderscript, if you write it in Renderscript and the phone itself has a custom Renderscript driver that is utilizing Vulkan, then you're doing Vulkan and you didn't even realize it. But we haven't used it, at least not at VSCO. Let's see, what do we got here? Script intrinsics. Do we want to talk about this? Yeah. I just want to get these out there. These script intrinsic functions are have a certain guarantees with them, which is this is the fastest possible implementation of these particular intrinsic functions that you can have on the phone. Blur, 3x3, 5x5 convolution, which you could use for edge detection, or sharpen maybe. The YUV to RGB conversion is pretty incredible. Lets you get camera frames. It lets the Renderscripts can get frames directly from the camera in a particular YUV format. You can convert them to RGB and edit them right away. That's what's happening in the app. Script intrinsic resize is like really fast. It's really fast bicubic interpolation. Like the interpolation it uses in the resize algorithm is bicubic, which is really nice, and it looks great. It's very fast. Script intrinsic blend is alpha blending, which you don't always have to. It doesn't always actually have to be the alpha value. You can use this to trick it into doing linear interpolation for you. You stash like some kind of scale factor in the alpha channel, and then you, I don't know, then you blend, but really you're doing whatever scaling you want to. I kind of like that. It's pretty tricky. Script intrinsic color matrix is one of these haloparallel edits. I think it can do edits in HSL. It has something built in where you just say set grayscale, and it just sets the correct matrix that you would have wanted if you wanted to get a certain grayscale edit, and it's a point edit. It's a pure color to color function. And then script intrinsic LUT, script intrinsic 3D LUT, I adore with all of my heart. They are it's an amazing. So for script intrinsic LUT, it's per channel. So that there's an array for each one. So the red, green, and blue can be between 0 and 255, and then you give it 256 values, like an array of 256 values for each one. The all possible answers are pre-computed, and it reduces the computation to an array lookup, and it's super fast. And you can do a lot of things: contrast, exposure. If you can ever get whatever it is you're trying to do into a LUT or a 3D LUT, I highly recommend it. 3D LUTs are also, would be like a color cube, which are pretty amazing in themselves. You can manipulate them as objects themselves, scale them, and combine them. There's a notion of multiplication, sort of like matrix multiplication between color cubes, and they're lists of colors. So it's just like, it's also an image. They're so wild. You can do such great stuff. I recommend it. All right, let me show you this. Okay, let me show you this video. So this is the Hello Renderscript. This is just the project that I did that I'm open sourcing. Okay, and it's got a cat in it. This is great. This is very exciting. It's not a very nice looking UI, but this was originally, I just put these flowers out because I wanted it to. Oh, it's not. Oops. Mm-hmm. Got it. Yeah. Okay. This is my cat helped. It was originally just going to be a video of some flowers. So this is a recording of the phone itself. And what we're essentially doing here is we're getting frames directly from the camera. The allocations are able to be surface consumers. So the first thing we're getting is we're getting a frame. The frame that's coming from the camera is some YUV format, and we know because we're setting up camera 2 to give us frames in a particular way. We're able to say, we want to consume the camera preview directly into an allocation with this YUV format, and then the first thing we're going to do is script intrinsic YUV to RGB conversion. And then we're going to do whatever we want with it. At that point, it looks a lot like a bitmap, so anything, the logic is sort of uniform at that point, whether it's going to be a bitmap or not. So this is 5x5's RGB sharpen, which is sort of like edge enhancement. Seems pretty fast. The Gaussian blur, tens of big radius, like that's a lot of work per pixel. Seems pretty impressive. It's dropping about every other frame. This is the script intrinsic, this is the resize, and what it's essentially doing here is there's another allocation. It's my favorite resize API, which is that you just give it another allocation that's a different size, and it'll just resize it to fit into the new one. So you make one that's about a quarter the size. You're going to have it resize into that one on the output allocation, draw some random color, and then do a copy into the center. And it changes at random every 10 seconds. Key rotation, this is pretty psychedelic. It kind of makes me car sick. But this is an HSL edit, so it's like in the cylindrical color space and it just sort of spinning around. Whoa, pretty. This is a mistake. So this is instructive. This is very about when you're doing image processing. Sometimes you make a mistake and it just ends up looking cool, which is great. Because this is an arithmetic error. It's clamping. It's hitting the top. Everything's sort of adding up to white. This looks cool. And those are those two together. It's a good old kitty cat. Anyway, so that's it. This is open source. I like this because it's sort of you have an RS renderer, which is, it implements a single function, which takes like allocation in, allocation out at a point where they look like bitmaps. So if you're using a bitmap, that will work. If you have, or in this case, it was inserted in the point in the camera pipeline where they look like bitmaps. But this is actually nice for testing out an edit to see if like, if you normally have a some sort of test application and you want to make sure that it looks good in a lot of cases, you're going to need to compare it with a bunch of photographs, where in this case you can just sort of like point it at things, point at something that's dark or something that's bright, or your friends, and I don't know. What is this? Open source, I don't know, go for it. Yeah. Let's see. Yeah, more fun than doing with maps, it's true. What else do we get? Renderscript itself, I guess, in general, script intrinsics should be common knowledge. I think that this is something that developers should have some intuition, at least that it's there. You don't always need to be editing bitmaps, right? But it's not that specialized of a case. I think that it would be a lot to assume that, be like, oh, you want to do it fast, so like just spin up, like make sure you just do it in a shader in OpenGL. Like that's a lot to ask. Renderscript intrinsic, like that's not. This is a high level Java API. It's sort of not, like the documentation isn't very good. There doesn't seem to be a lot of examples out there, but it is absolutely a robust technology. We've used it at VSCO for like 3.5 years. Our entire photo pipeline is written in this, and it's been, I don't know, it always like seemed like a risk, but it's just been pure value for us. We've been able to get a huge amount done. So like from the engineering justification is like, yeah, this is like you can do pretty incredible parallel compute with a morning of work, which is useful because probably you're not just on an imaging team, like you have other stuff to do, like maybe somebody books sign-in and you have to triage that, right? But so it'd be like, well, I want to do blur, but I don't have a week, I don't know. Issues is legitimately poorly documented. It's difficult to debug if you write the custom kernels in the custom Renderscript language. It's sort of hard when things go wrong to tell. Not quite as hard as when you're using OpenGL and it renders black to the screen and you're just like, okay. But the logging isn't particular. You can't sort of step through it in the same way, and you can also get like segmentation faults that are a little bit difficult to debug. Let's see, what else? I don't know. That's basically it. I don't know. I guess I had a little bit of the documentation from the. So for the project, it's essentially like this is what the interface looks like. If you make a RS render and it works well in this program, it will work identically well for a bitmap. So however it is that you want to use it, it can. So the application is about 70% other Google example code, with the parts that are less interesting, less germane to understanding the core of the framework, kind of pushed aside and like, let's talking about this. Cool. I think that's all for me. So, thanks so much for coming out. I want people to use this technology, and we can all be, answer each other's questions on the internet and be friends and sort of. I don't know, I adore this technology, and so I recommend you check it out. Thank you.